first introduce myself. I'm Gao Qianzhong, National Taiwan Normal University. And we should begin with the introduction of the team captain, with his team members. Let's begin with the reporter team, Mirabel.
Good morning, professors and fellow competitors. We're Team Miracle from Jianguo High School. I'm the captain Wu Zhenwei. This is Zhang Yachen, Yang Yaohan, Chen Yanli, and Ye Zhong.
Then the opponent team, Google.
One majority for the competitor and the most guy. I'm the captain of Team Google. We're representing our school, Yao Shinwang High School. And this is my teammates, Wang Yixi, Ren Hongyu, Zheng Yixi, and Chen Boyi.
And the reviewer team.
Hello everyone, we're Team Synchronized, and we're from Antiphase High School. I'm your captain, Typt, and this is Synchronized, Zhang Changwei, and Xie Zhong.
Okay. Let me introduce the juror members. Let's begin with Professor Song Zhenyi from National Yangming Jiaotong Professor Lin Zhifeng from Taichung University, and Professor Mo Zhongyu from National Tsinghua University, and Professor Xie Li from National Zhongzheng University, and Professor Li Weijun from National Taichung University.
Yeah.
So let's begin with the challenge process. So challenge opponent team.
We'd like to challenge problem number 5, Synchronized Normal.
Problem number 5. You have 1 minute to complete it.
The reporter accepts the challenge.
Okay. Problem number 5, accepted. You have 5 minutes to prepare. In the meantime, each team should send a member to write down the representative of the team and write down his or her name. 哪一个？名字连到哪？对，连到哪一个？连到这个。现在是连不上去，按这边切换出来。
Good morning, dear professors.
等一下，没有说开始。Sorry。
就是我们电脑出来还有一个接外接信号，那这边我们可以做到就是
你等一下，他们中间休息的时候再继续。Okay, let's begin with the presentation.
Good morning, dear professors and fellow competitors. My name is Arthur Chung, and I'm from Wheelbarrow. I'll be reporting problem number 5, synchronized candles. Here's the problem introduction. Oscillatory flames can be observed when several candles burn next to each other. Two such oscillators decouple with each other, resulting in in-phase or antiphase synchronization, depending on the distance between the sets of candles. Explain and investigate this phenomenon. Notice that the two such oscillators here means the bundles of candles mentioned above. So we have 3 key questions. How does the air flow? What causes this phenomenon? And what is the relationship between the distance and phase shift of the candles? This is my presentation outline. First, I will show you the phenomenon, demonstrating the oscillation and the phase shift. Then I will show you our oscillation analysis, and I will show you the definition of 3 types of motion. Then I will introduce our theory about the energy of the flame and the parameters and our theoretical lines. And then I will show you the air dynamics, using Schlieren method to film how the air flows around the candles. So this is our phenomenon. On the left is the in phase. As you can see, the candles oscillate together. And in the middle is rotation. It means that one bundle of candle slightly lags behind the other. And on the right, you have antiphase, which means the candles oscillations are completely opposite. And this is our experiment set up. We mounted our candle bundles onto this apparatus. And then we turn the knob to control the distance between candles. We put a box over it to minimize the effect of the disturbance of outer air. And then we film the flames of the candle through this window, created with a transparent tape. And we use tracker to analyze the brightness of the candle. And this is our analysis. As you can see, in phase, the brightness of the candles move together. In rotation, one slightly lags behind after the other. And in antiphase, the brightness of the candles are completely opposite. And notice that as the distance increases, their phase shift also increases. So when we plot the phase shift to the distance between the candles, we can see that the phase shift between the candles starts to increase. You see there, when the candles are very close together, their phase shift is really, really small, which means that the candles oscillate together. And when they get slightly apart, their phase shift gets bigger, and it results in rotation. And then when the phase shift reaches its maximum, the candles reach antiphase, which means the candles oscillate completely opposite. And then when you take them even further apart, you can see that there's no coupling. Notice that the error bar here is very, very large. It means that the candles are not related to each other anymore, and that so that their phase shifts can vary. And this is our theory. We got this theory from a paper, and they say that they want to explain the oscillation of a candle bundle first. They think the oscillation of this is our equation, and they want to describe the oscillation of a candle with energy. And this equation is divided into 3 parts: the transport of heat by flow, heat production by combustion, and energy loss by radiation. So these two take energy away from the system, and this adds the energy. And on the bottom here we have how oxygen affects the combustion of the candle. The way they explain why a bundle of candle oscillates is with the comparison of fuel supply and oxygen supply. A here is the fuel supply of the system, and then Ni is the oxygen supply. So if A becomes too great, meaning that fuel supply becomes too great, then the candle will burn brighter and bigger. The flame will burn bigger. But since the flame burns brighter and bigger, it will consume more oxygen. So there will be less oxygen in the surrounding air. So the flame will decrease. And when the flame decreases, the oxygen it needs decreases. So if the flame grows up again. And they also explain why two candles oscillate together if you put them further apart. The thing is because of radiation and how energy transfers from one candle to the other. And this is the theoretical line plotted with the equations in the last page. And on the left, you can see that the candles are put closely together. And this is this is the theoretical graph for a bundle. And as you can see, the candle oscillates. When we make the fuel supply bigger, the candle oscillates. On the right, you can see this is the example when we move the candles further apart. And because of the radiation and the heat transfer, the candles oscillate in antiphase. And notice that the distance between the candles and in phase is 50 millimeters, and the distance between the candles and antiphase is 30 millimeters. And if we look here, in our experimental data, the distance between the in phase is about 20 to 30 millimeters, and the distance between the distance for the antiphase is about 40 to 70 millimeters, which means that theory does not fit with our theory, fit with our experimental data. So we want to see what other factors may be affecting this motion. So we think it might be the airflow around the candles. In order to know how the air flows around the candles, we need to use Schlieren imaging. So what this is that we use a point light as our light source, and put it at a focus of this convergent lens. And the light becomes parallel after it passes through this lens. And because of density difference in this region, some light refracts, and the light passing through this part is collected by this lens, and it converges on the focal point. And because some light is refracted, we put a sharp object here to block off the light, and we can pick up the remaining light with our camera, so we can see the light and dark parts in this region. And that represent the density difference, which will represent the airflow. And here you can see in phase. Notice the vortices here and here. Because our camera is slightly off, our candles are here and here, the bundles of candles. So we want to focus on these vortices and these ones. Notice that they rise simultaneously. And in antiphase, notice the vortices here. One rises on the right, and then one follows on the left, and one follows on the right. So this pattern is different from this pattern. The vortices rise simultaneously, rise on the same level here, but the vortices are crisscrossed here. That's the difference between the vortices of the in phase and antiphase. So this is a diagram demonstrating what I mean with our Schlieren imaging. Because the flame heats up the air around it unevenly, the rising velocity of the air is uneven. And the And velocity difference causes the air to form vortices. And this vortices will shape the flame as it rises. Because the flame in phase is, the candles in phase are put closer together, the velocity difference of the air inside here is lower. And because the flame in antiphase are put further apart, the velocity difference in between the candles are larger. So the vortices will be stronger than the vortices in the in phase. And now I will explain how the vortices in the in phase shape the flame. So as the vortices form at the bottom of a flame, which is the hottest part, they rise simultaneously, and then as it moves upward, it stretches the flame, and makes it seems to be oscillating, and ultimately cuts the flame off. And because the velocity difference, the two flames are very close together. Their vortices should be at the same level, so the oscillation should be the same. And in antiphase, because the vortices are much stronger, any disturbance can cause them to be at different levels, and they won't be returned to the same level easily. So they end up in this antiphase. And in our conclusion, we observed the phenomena of candles oscillation. And in our experiment, the phase shift increases as the distance between the candles increases. For in phase, the range is about 10 to 20 millimeters. For antiphase, the range is about 40 to 70 millimeters, which is different from the result predicted with the theory with radiation. And so the oscillation is caused predominantly by vortices and not by the radiation. And what causes the vortices to form? The velocity difference of the outer and inner airflow causes the vortices, which affects the oscillation as the vortices rises. And the velocity difference depends on the distance of current boundaries. The different modes of vortex lead to a different phase shift. Thank you.
Okay, good morning, honorable judges and fellow contestants. I'm the opponent for problem number 5, Synchronized channel. Okay, so first, can you show me page 8?
Page 8.
So you have no coupling here, and in your videos you show in-phase rotation and anti-phase. Do you have a video showing no coupling phase?
No, we don't think. No, we don't have a video here.
And also, can this rotation phase be like a transfer between in-phase and anti-phase?
Yeah, it definitely is.
And also, how many candles did you put in a bundle?
3 candles.
3 candles. Okay. And did you put all the candle wicks together?
No, we only put them very, very close together and make the flame like the same as one. So the flames, it's actually a cluster of flames. There's no space between the flames.
Okay, so it's just one flame burner.
Yeah, yeah.
Okay. And also on page 12. Okay, can you give me a quick explanation about the colors?
The colors. Oh, the color is caused by the dispersion of the lens. It's a byproduct of the Schneider imaging.
And also, I would like to ask, so when the candles are burning, do you control the height of the flame?
Do I control? The height of the flame is the result of the oscillation, so we don't want to control that.
Oh no, sorry. I mean, when they're like burning.
The height of the candle?
Yeah.
Yes.
Okay. And is this a result of the candle wax flame?
The candle wax flame? You mean the height?
Your time is up. You have 3 minutes to prepare for your discussion.所以我要提醒大家，就是在竞赛期间不能连到网络上。
Okay, honorable judges and fellow contestants, I'm the opponent from Team Google. And today the problem I'll be opposing is problem number 5, synchronized candles. And here's the problem statement. So the problem wants us to investigate auxiliary flames and also the two phases which are in phase and antiphase. And the reporter also mentioned another phase called rotation phase. And also the phase shift and also the distance between two candles. And here's the outline and summary of the reporter's presentation. So for the phenomenon, the flame of the candles will oscillate in phase or antiphase mode. And also the laws applied are the energy equation and also the using oxygen supply and combustion to as their theory. And for the setup, candles were used, also camera, tape, and lenses. And the parameters that were done were the distance between the two bundles of candles. And one of the main results is that the different distance between the two bundles of candles will cause a phase shift in the two oscillations. And here is my comment and summary of the report. It was a good presentation, and the reporter showed his theory and also how it compared with his experiment. And I think the theory was quite complete. And for the suggestions, I think the reporter maybe can try do more comparison between his experiment and also the theory. And here is the summary of questions of discussion. And okay, so for the theory portion, I want to ask more about the equation of flame energy, and also what point they track in the flame, and also is there a section that no oscillation occurs? And in the setup portion, I asked this in the short questions, how they set up the two bundles of candles. And for the experiment, I want to ask more about the airflow differences between in-phase and anti-phase motion in the video. Okay, thank you. Okay, so now the time for my discussion. So, can you show me how did you track the candles?
Yeah, I track the candle by marking this region here. So it takes the average of the brightness of this region, and yeah, it takes the brightness of this region average.
Okay.
And yeah, this is the middle part of the flame.
Okay, so you use the brightness and to average the point.
Yeah, yeah.
Okay, thank you. And can you turn to page 10? Okay, so as you can see here in the antiphase, the amplitude of the two candles seems to start to decay.
Oh.
And is this maybe caused because of the oxygen used?
It might be caused by the oxygen use, but it might also be caused by the radiation loss when it's not transferred to the other candle. So it's a combination of all these variables.
Okay, and so do you do all your experiments in an isolated environment?
Yes.
Okay, and also for the
but oxygen is allowed to flow into the system. So this the oxygen does not decrease constantly.
And the next thing I would like to ask is, so when the candles, you control them to have the same height,
Yeah.
the rest of the flame, and this causes different velocities of the airflow. It causes vortices.
Yeah, yeah.
And so I would like to ask, maybe if the flame height changes, there might be would there be a different oscillation state?
With the flame height changes. What do you mean by that? Do you mean one candle is higher than the other?
So in your experiment, you seem to control the height of the flame, right? So when they're not burning together.
But they're not burning together. Control the height of the flame. I want to observe the height of the flame, and the height of the flame is caused by the vortices. So
that's good. And also, so in your theory, can you turn to your theory page? Okay, so here in the second line you talk about the oxygen and also the combustion the consumption of the oxygen, right? So I would like to ask, if there was a candle, only one candle that maybe used a lot of oxygen, would it oscillate?
yeah, could you come to the black board? So if I had a very, very thin candle, and according to the equation, its fuel rate, which is A, and it's small. So the candle will not oscillate. So the equation, the theoretical line might be like this. But if I had a very, very thick candle, and then it has more region to heat up, so the fuel rate might be bigger, then the theoretical line will seem like this. So this is the same to this if I had a bundle of candles together.
Okay, thank you. And also, another thing I want to ask is, can you turn to the page where you have in-phase, anti-phase, and rotation? Yeah, this one. Okay, thank you. So you seem to have to keep increasing the distance between the two candles. What if you shrunk the distance between the two candles?
Could you repeat that again?
So here in phase, the distance is like about maybe 15 millimeters.
Yeah.
What if the distance between both of them was less than 15 millimeters?
We didn't try that because that would be really hard. Since the fuel rate, the candle will have to be very, very thin. This is the distance between the center of the flame. So yeah, so the candle will be very, very thin.
And also, so in your presentation you mentioned that the theory doesn't quite apply to your experiments, is that correct?
Yes, the radiation one.
So only the radiation line?
Yes, only this part. Only this part. Yeah, you see this is the distance between the two candles. So if this is really, really small, it means that the candles are in a bundle, which we can treat it as a single flame. And if it is a single flame, then the most important factor is the fuel rate, the fuel supply rate, and the oxygen supply rate.
Okay. So in your experiment and the theoretical, did you try to make the two conditions as similar as possible?
You mean
So when you're drawing your theoretical line.
theoretical? You mean this and my experiment?
Yes.
Well, there are some deviations, but here I'm just trying to show you that the reason a bundle of candle can oscillate.
Oh, okay. Thank you. And can we turn back to where you showed the phase shift difference between in-phase, rotation, and antiphase?
This one?
Yeah, this one. Thank you. Okay, so in rotation, will the phase shift change over time and become become in-phase or antiphase?
Become in-phase or antiphase? Yes, if there is disturbance, it's our disturbance, but if we keep it in an isolated system, it will remain like this for a pretty long amount of time.
Okay, so by disturbance, do you mean maybe like airflow disturbance by
Yes.
the environment? Okay. And so this will cause it to change into in-phase or antiphase?
Yes.
Okay. So then the distance will the distance still play a big role in?
Yes, the distance affects how stable the system is. So if the distance is longer, the vortices are stronger, which means they cannot be lined up.
Okay. So in your antiphase picture here, so what causes the amplitude to have such a difference?
Well, you mean this one? Okay. Yeah. It might be the radiation, and it might be the oxygen supply, but we're not sure about this one.
Okay. Do you think it might be caused by some vortices caused by the two candles?
Yes, it might. Yeah.
Okay. Okay. And can you turn to your observation video with the in-phase candle? Okay. Can you play the video? Okay, so as it's burning, there seems to be a flame eruption.
Yeah, can you come to the blackboard? So the full process of the oscillation of flame starts like this. When the candles are close together, the velocity of the airflow are consistent in this region. Do you agree? Yeah, the velocity.
The velocity is consistent.
Yeah, in this region, pretty consistent. But the velocity in this region, in the outer region, is not consistent. So when this velocity difference, it creates force, and it creates vortex. And when this forms, it rises, and it rises because the surrounding air is rising. So it rises and it squeezes the flame in. So it starts like here, and then squeezes the flame in. It might look like this. Squeezes the flame in. And because it squeezes the flame in, the air was rising consistently in this part. And they encounter this boundary. So they encounter this boundary. So that they form vortices here too. So as these two vortices rise, they start to squeeze the flame together. and yeah, because the energy concentration is not that high, it's easier to be broken. And so you end up with this part, and the flame is broken.
Okay, so it's basically the vortices squeezing on the candle flame.
Yes.
And causing it to.
Yes.
Causing to. Okay, thank you. And for another question, since you seem to have put a box over your in your treatment, right? And what would happen if you remove that box?
What would happen if I remove that box? I would assume that the outer air disturbance would be greater, so our phenomena would be harder to observe. I think that's what will happen.
Okay, so it might be hard to observe all these phases.
Yes.
Okay, thank you. And also, so in the in-phase rotation and antiphase, did you do these experiments? Like, did you control the distance and then shoot the video and then turn off, do it again by changing the distance again?
You mean, did I continuously pull the candles apart, or did I like set them here and then set them there?
Yes.
Okay. I used the second method.
Oh, you use the second method. Okay, so why didn't you want to try maybe using a dynamic way of changing the distance?
Oh, we also tried that, but it's like the moving motion of the candles just makes the system unstable.
What if you moved it and placed it there for a while? Or maybe it would start to become more stable.
Yes, we did try that for a few experiments, and sometimes when the candle bundles are really close, they start out at in phase, and then as you slightly move them apart, they still remain in phase, but as the time goes on, as any slight disturbance will cause them to move into the rotation phase or antiphase.
And last question. So you're in phase here. There seems to be 3 flames burning.
Yes.
But you mentioned that you put all the candles together to make one flame, right?
Oh, this is just these are bundles. These are bundles of flames. As you can see here, these are bundles of flames.
Okay. You must stop here. Okay.
Okay, so I'm going to conclude our discussion. So I asked him about the 3 different phases, in-phase, rotation, and antiphase, and how what's the difference between them, and also I learned that the vortices are the main reason of these oscillation phases, and there was also how they conducted the experiment. They used 2 bundles of candles to observe this phenomenon, and also that oxygen was a main factor in their experiment. So the combustion and consumption of the oxygen and also oxygen supply is a big factor in this experiment. Thank you.
Okay. Now let's move on to the reviewers. 你这个是不是要切换过来？
Thanks for the report of the reporter and the questioning of the opponent. So the first question I want to ask the reporter, like, because you said you were tracking the height of the flame.
The brightness.
Brightness. So how do you identify like the height of the city? How do you track or identify the height each region?
Oh, the brightness here is related to the heightness and to the heightness of the flame. So and if the flame is stretched, then the brightness it won't be that bright. The energy concentration won't be that high.
Okay. And the next question is that you said that in the experiment that said that the height for one side you use 3 candles. So did you try using 2 or 1 candle on each side, and do you think that it will affect the experiment? Okay.
So I think it will affect the experiment. Maybe it will affect the candle flame's height and also the consumption of oxygen. But I don't think it will affect the 3 oscillation.
Yeah, I also agree that it won't affect the oscillation. It might affect the oscillation if you put them really close, because of this equation. Then the A will change and the N will change too.
Okay, do you think that the convection or the heat transfer in the experiment will be a factor of this experiment?
Yes, in this equation, we did include the transport of heat by flow and the convection. Oh, convection. Yes, it will affect the motion of the candle, but the main factor, the main variable we're trying to observe are the vortices. So the vortices and the rise of air are caused by the convection.
So did you put the factor or the effect of convection in
In our theory,
Yes.
no.
Do you think convection will affect?
Convection, I think it affects the airflow around the candle.
That's my question. Thank you for that.
您的线可以拔起来，让它们是上的哦，可以拔掉，拔掉。
那个没有显示只有50个。
你拿过来这边接接看。
那边先厉害。
用这边的线接接看。
有啊，对啊，所以要么就是这个线有问题。那没有，只要换这个 HDMI 的线就好了。哦，好。可以吗？用直接的。那可是还是没信号。OK， 先这样，等一下休息再说。那你就 OK， are you ready now？
everyone, I'm the reporter Austin Chen, and I'm reviewing problem 5, Synchronized Candle. And this is the outline that I'm going to be going through today. And the problem statement, so this is the problem statement, and the reporter's focus is on the airflow's motion and what causes the phenomenon. And this is the overview and the summary of what the reporter said. So the phenomenon are in phase and rotation and antiphase of the flames. And they use the theory in energy equation and the oxygen concentration, but they found that it doesn't matches with their experimental value. So they uses the Sclerin method to explain with the airflow velocity and motion. And this is the experiment value and compared to the theory value they presented in their presentation. And for the reporter, I think they have clear footage demonstrated with a video, and the Sclerin method used to when the experiment result doesn't matches their theory. And they explain the condition of airflow with in-phase and antiphase conditions. And the weakness is that they don't have a video for no coupling. And I think the opponent provided many valid questions. So I'm going to talk about the discussion. And the first question is that when the candles are very close and they will burn into one flame. And the reporter said that it is considered in the experiment, but it does not affect the value of the experiment or the results. And the discussion two is how is the candle tracked and how is the height is tracked. The experiment used the tracker to track the brightness of the candle. And for the third discussion is the opponent asked in the graphs why does the energy start to get decayed, like the show in the amplitude of the energy. And the reporter said that the energy will decay maybe due to energy loss or radiation, causing the amplitude to vary or to change. And the fourth discussion is distance less than 15 millimeters considered in the graphs, because at the graphs they didn't show distance under 15 millimeters. So the reporter said that the flames would be too close because the distance is measured at the center of the candle. And the fifth discussion, will rotation change to other phase as time passed by in the experiment? And the reporter said that if there are disturbance when they are doing the experiment, the rotation will change to antiphase or in phase. But since they put a box in their experiment so that the experiment is isolated, so there are not many factors that will affect the rotation. And the next discussion is that what causes the amplitude to change in the antiphase, which are shown in the graphs. The reporters are not sure, but since the change is not that large, so they believe that there are other factors, but it is not that important or that significant. Yes. And these are the points missed or that I discussed with both. So I think that maybe convection of the candle can be discussed during the experiment. Maybe it will affect the height of the candle or the flames, and maybe changing the amount of candles on each side, like tying 1 or 2 candles, not 3, is fine. Thank you.
So concluding remarks. We did experiment in non-isolated systems, and we did see demonstrate our phenomenon in this case, but it's still unstable. That's why we switched to isolated systems. And we observed the isolation through the average brightness, not the highness of the flame. To simulate the convection on an airflow in the real world will be too difficult, so we can only qualitatively explain the phenomena with our theory. And the deviation between the theory and the experimental data is not, the deviation is the reason we decided that the radiation is not the main factor. You can see that in our experiment, the range for antiphase is about 40 to 70 millimeters. But in our theoretical data, the range between the candles is about 30 millimeters. and it switches to no coupling when the distance is above approximately 45 millimeters. So because there's a difference between the theoretical and experimental theory, we decided to investigate the airflow. And the candles we use will not oscillate if there are only one. That's why we tied them in a bundle, just as the problem stated. And all we want to see in our theoretical line is the distance needed to create antiphase. And the last question, if you put the candles very, very close, then that is the same as a bundle where you just even a single candle. Thank you.
Now let's move on to the question of view. Okay. Any question?
Okay, let's back to the black hole. When the candle is small or large, will that affect your result? That you have discussed, right?
Yes.
Will that affect your result?
If the bottom part containing the paraffin is larger, then that would affect the result. Maybe the oscillation will be bigger.
Then we'll ask the next question. If you change the flame, the core of the flame to be bigger, then the flame will be much larger. Will that affect the result?
Yes.
How?
Then
let me reframe my words. Will that oscillation distance, in phase and out of anti-phase, the distance will be larger or smaller? Let's go first to the opponent.
Okay, so you're asking if the flame height is larger and the distance.
Yes.
I think that the distance will become smaller.
Reviewer.
Maybe I think I agree with
I think it will be smaller
Why?
because the convection will be stronger.
Okay, let's take question from another theologian.
Yeah, I think you also noticed that I want to ask the question, what is the main cause for the oscillation?
The oscillation is
So starting from you, I mean, so you told now it's not radiation, so I was thinking vortex is the main cause.
yes.
Or the vortex is a consequence.
Yes. So
Which one? I mean,
it's the
vortex is a consequence of oscillation.
The cause or result?
the heating, the uneven heating of the air around the flame causes the vortex, and the vortex shapes the flame as it rises.
What is your main reason for this conclusion? Do you have any?
The temperature difference causes the air to rise at different speeds.
So I mean the experimental evidence is showing you that's the cause.
Okay. So when we move the candles further apart, then the velocity difference between of the air between the candles can be greater. So the vortex will be stronger. That's because the vortex are stronger, then their effect on each other will be stronger. So when a slight disturbance occurs, then they won't be able to return to the same level because the vortexes will crash into one another. That's why they will become like this. They will rise in this pattern.
What about?
What causes the oscillation?
Which one is the cause? Yeah, the main cause.
I think it's the airflow.
So you are thinking also vortex is the main cause. Okay.
I think it's also there.
Okay. And okay, another question is for the theoretical, but your theoretical calculation also showed the oscillation, right?
Oh, yes.
Your theoretical calculation, do you calculate three frames or just 2 frames?
2 frames. You mean the time?
The calculation.
The equation.
The equation.
Yes, this one.
This equation is actually wrong. I mean, the last term is actually not quite correct.
This one?
You have an IJ in first equation. You have IJ. I is equal to 1, 2, or 1, 2, 3.
This one.
Yeah. The parentheses should be inside, and also how many frames we calculate?
Frames. How many frames did I calculate? I don't quite remember. How many frames did I calculate?
You calculate three candle or two candle.
Yeah.
Okay. How many frames? So if this is okay. So this distance is the oscillation this theory is trying to explain is the distance is the oscillation of one candle and the other.
Only two.
Only two, and they are apart.
But your experiment is three candles.
Okay. Can we because when we tie the candles in the bundle, the A increases. So if we decrease the A, if we increase the A here, it means that it's the same as to tying two bundles of candles together.
Okay, we have to stop here. The time is up. So let's now move on with the grading. let's begin with the grade of the reporter. Starting from me, it's 6, 9, 7, 7, 8, and 6. Now let's move on to the opponent. Starting from 6, 7, 7, 6, 9, and 6. Finally, to the reviewer. It's 5, 7, 6, 6, 7, and 5. Okay, so maybe we can have some remarks from the viewer. For the reporter, anyone?
Careful about this preparation. Yeah, I
Yes.
don't think you have done right preparation.
Yeah, right.
So,
And you fall in love with your equation, and you not really understand the equation, then there's no, actually the equation doesn't include the vertex part. So you have a problem. Your problem is related to the vertex, the flow of the airflow.
The reason that I give a 6 is that I think that you seem that you didn't try to change, control the various parameters, because probably the size of your candle is always the same, right? You didn't try to change the size of the candle, and that if you change the size of the candle, then the distance probably will change, and probably that will give you more evidence to argue your result. And for the opponent,
yeah, my comment is because that's related to my question. The main cause, which one is the main cause? That should be one of the main points you should try to figure it out, right? And the total, like you say, it should be a vortex, then you should, check this part. How do you conclude that it will vortex?
For the reviewer and opponent, I think you didn't present your own opinion.
Yeah.
You just ask questions and
You will notice this part, but somehow you don't have your opinion.
yeah, and my suggestion to the opponent is that you seem to touch on some on many points, but you didn't focus on the more important one. You should probably spend more time on the important one, not just jumping around topics. That doesn't help us understanding the whole thing. Anything else to add?
Yeah, I think to see whether the vortex is the cause, you should try to look at the time. Whether the oscillation starts first. Starting the time of the oscillation started and the time of the vortex is noticed. Which one is occur first? That's more direct evidence is done, right? If you see the oscillation start first, then that's the cause. If you see the vortex start first, that's the cause.
Okay, if there's nothing more to say, then let's conclude this
Okay.
stage. We have 10 minutes break.
Opponent want to challenge problem 7, B dynamics.
Problem 7.
So we reject.
Okay. The problem is rejected. Problem number 7.
Opponent wants to challenge problem 9, Lewis.
We'll reject it.
Again, rejected. Okay. Problem number 9.
Opponent wants to challenge problem 17, Pen helicopter.
And helicopter.
We'll reject.
Wow. 17.
Rejected.
Rejected. Okay.
Opponent wants to challenge Problem 12. Well,
Problem
Wilberforce.
Will accept.
Okay, problem number 12, accepted. You have 5 minutes for the preparation. Please write down the name of your representative on the platform.
Guo Chen from Team Google. And today the problem I'll be reporting is number 12, Wilberforce pendulum. So here's the problem statement. A Wilberforce pendulum consists of a mass hanging from a vertically oriented helical spring. The mass can both move up and down on the spring and rotate about its vertical axis. Investigate the behavior of such a pendulum and how it depends on relevant parameters. So in the problem statement, the phenomenon we're trying to look at is the up and down movement and also the rotating movement of this pendulum. And here will be the main focus of the presentation. So the first is what causes this phenomenon, which is the moving up and down and also the rotationing movements. And also creating the Wilberforce pendulums ourselves, and also the investigation on parameters and how it affects this phenomenon. And here is the outline of my presentation. So here is my observation video. Okay, so as we can see here, this is a Wilberforce pendulum. And when we give it a longitudinal displacement, it starts to move up and down. But also, another thing we need to notice is the rotating movement. And as you can see, when the longitudinal movement starts to decrease and slow down, the rotational movement starts to speed up. And here we can see that it turns into pure rotational movement without longitudinal movement. And after a while, it starts to move up and down again without rotation. So it changes between these two modes, pure longitudinal movement and pure rotation. And here is the theory. So I'll be using, so the first thing I'll be explaining is the energy transfer that causes this phenomenon, and also the beat frequency, which is also related to energy transfer, and also the equation of motion. Okay, so first let's talk about the energy transfer. So as you can see in this video, we have a Wilberforce pendulum, and now we're pulling down on the Wilberforce pendulum. And you can notice that it starts to rotate when we pull it down. And this is due to the structure of the spring, which is a helical spring. So when we pull the spring down, it will uncoil. And when we compress the spring, it recoils. And it is this spring structure that causes the energy to transfer from rotational to longitudinal, and also from longitudinal to rotational. And here is an animation. So for the equation of motion, so for the longitudinal motion, we can see that it is written like this, and for the rotational motion, we can see that it is written as this. But another thing to note is that this is a coupled oscillator where it depends on the longitudinal movement and also the rotational movement. So we need to add a coupling constant to couple these two equations together, which can make the coupling oscillator. And here are the values for the natural frequency, which are for omega z is for the longitudinal motion, and omega theta is for the rotational motion of the spring. Okay, and so now we're going to look at normal mode frequency. So after solving these equations, we can obtain the two normal modes that are written as this. But the main focus will be that the beat frequency is equal to the difference of these two normal mode frequencies. Okay, so a brief introduction on normal modes. So it is a part of the oscillation system. So as you can see in this example here, one of the normal modes, which is the first mode, we can see that both of the masses are displaced in the same direction and also the same displacement. And the second is they have the same displacement but in the different direction. And so these are the two normal modes, and the general motion of the system will be a superposition of these two normal modes. So how can we use this in our theory? So we can see in the top one here, this is from a reference paper, and we can simplify it to a cosine plus b cosine. So we can use this as the normal mode, and this is the superposition of the two normal modes. And the B frequency here will also be the difference between the two normal modes. Okay, so now let's look at what this would look like. So in this video, I'm going to show that we're changing the amplitude of one of the cosine waves, and we can see that it starts to shrink, it starts to grow, and also starts to shrink. And this is due to the difference in amplitude. And here, what I'm going to try to show in this video is the difference in the frequencies. So as you can see, it seems to be compressed and also decompressed. Okay, so now comes the part 2, our experiment, where we recreate the Wilberforce pendulum. So let's first talk about our setup. So we connected the Wilberforce pendulum to a tube on the bottom of these two racks, and here is our Wilberforce pendulum. So we used a wooden rod and also 2 cylindrical weights on each end, and there is also a circular weight attached to the middle of the wooden rod. Okay, and here are some specifications of the Wilberforce pendulum. And as you can see here, we can change the moment of inertia by changing the distance of the 2 weights. So what I mean by distance here is that the center of mass of the cylindrical weight to the rotation of axis, and that is the distance. And here is an experiment video. So as you can see here in our experiment, we added a weight and also a string on the Wilberforce pendulum to make sure that we pulled it down straight, and we also used fire so we can control this. And this is for the longitudinal motion we can observe, and this is for the rotational motion. So here is our experiment data, and as you can see here, the red line represents the theta to time, and the blue represents the longitudinal movement to the time. Okay, and here the distance is 3.55 centimeters, which is the distance of the weight to the rotational axis. Okay, and now let's take a look at what happens when we move the weight to the further end of the wooden rod. We can see that the z of t, which is the longitudinal motion, seems to not go back, as we can see in the first experiment. It doesn't go back to 0 here, and it stays at the lowest point isn't 0. And we can explain this in the previous video where I showed the amplitude difference and what happens when different amplitudes are added together. And also, another thing to note is that the frequency seems to start to be compressed and compressed. And we can further see this trend more in as we move the weights further away from the rotational axis, as you can see here. Okay, so here we're going to give a data analysis of the data that we collected from our experiment. Okay, so here is our data. So on the left side is our experiment data, and on the right side is a fast Fourier transform on the theta of t data. And so from here we can obtain the 2 normal mode frequencies, as we can see on the last line here. And another thing to note is also I put the natural frequencies on the first line, and we can see that the B frequency we obtained from this graph is about 0.2489 radians per second, and from the B frequency we obtained from the fast Fourier transform is about 0.2660. So it matches quite well with our theory. And here is our data analysis for the second data. And as you can see here, the B frequency starts to increase, which means the energy transfer period starts to decrease, and the energy transfers between these 2 modes faster and faster. And this trend continues on as we move the weights further and further away from the rotational axis. Okay. And for our next experiment, which is experiment B, here we can recall this equation of motion that was in the previous slides. Okay, so in this experiment, we're trying to obtain the two normal modes. So to get this normal mode, we had to create an initial condition that that one of these cosines, the amplitude was 0. Then we can obtain the normal mode. So for the first one, it is the symmetric normal, which means the rotational direction is the same with the spring. And here are the conditions that have to be met to create this normal mode, as we can see here. And in this data, we can see that there is still a slight coupling in between the two modes, but it's almost close to just one cosine wave. And as we can see here in our fast Fourier transform, it also agrees with our observation. And here is our second experiment, which is the antisymmetric. And there are also similar results, but also here are the conditions. But the other thing is that it seems that the coupling effect here is stronger than our symmetric one. And I think this is due to the spring's structure. So now is our conclusion. So when the difference of the natural frequency increases, the B frequency increases, which means the energy transfer period is shorter. And also the natural frequency is the main variable in the Wilberforce pendulum. And here are the references. Thank you.
Okay. Questions from the audience?
The first question I have, can you please turn to page 19?
Thank you. This page?
So this is our experiment video, right?
Yes.
So, can you play the video, please?
Sorry.
So as you can see, your wooden rod is tilt. So, but I believe that your releasing condition is pretty stable.
So what causes this tilt in the wooden rod?
Yes.
Oh, I think this is also due to the structure of the spring, since it is not symmetrical, and it will cause a slight tilt in the wooden rod.
And second question, what is the material of the mass?
What is the material of the mass? I think there are some metals inside the weights. I found this in the laboratory.
So it is
It is a metal.
a metal. So you didn't check it is if the mass is evenly distributed?
I think the mass is evenly distributed.
Okay, and my third question is, so you've got coupling and anti-coupling, so there are like two extreme conditions. So did you do graphs when it is inside the extremes?
Sorry, can you explain the?
Maybe we can continue a little bit later. We have 3 minutes to prepare. Please begin.
I'm the opponent from Team Limited, and this is our an application of work. So the problem statement, they mentioned that the important point here is the mass can move both up and down on the street and rotate. So they are going to investigate the two things. And so about their summary, so on their experiment, they got they released the pendulum. They released the pendulum by burning out the line connected to the mass hanging on the pendulum, and I think that is a really good thought, because that could avoid the pendulum swing. But I think they don't have a their experiment setup their material isn't stable enough, because as they say, they just got a piece of metal from their laboratory, and they didn't discuss and do the relevant parameters, such as different mass hanging on the pendulum, or the mass hanging on the wooden rod. And of their theory, I think they've done a good job on predicting the motion and graphing out theoretical results with their equations. And they've analyzed their prediction based on their theory good, but I think maybe they can do a bit more on the compare and contrast between their theoretical results and their experimental results. And so they've done. So some questions I would like to discuss is, first of all, because of the tilt of the wooden rod, like as that is their stern wheel, so it should be, everything should be accurate and correct. And maybe the prediction of if they change the mass hanging on the pendulum, and how would that affect the phenomenon? And since they have every correlation with the frequency and amplitude, like every graph is on different slides, so I would like them to summarize again how the frequency and amplitude correlates, and I think we can start the discussion.
Okay, please move on.
So my first question, can you explain again why the wooden rod is tilted?
The wooden rod is tilted. As you can see, I think it is a combination because of our camera setup, and also because of the spring structure.
Have you considered maybe it's because maybe your mass wasn't evenly distributed, or maybe like since you got two mass stacked on the wooden rod, right? Maybe their distance to the center of mass wasn't equivalent, so that would make a different rotational inertia.
No, I think it was evenly distributed.
And the second question, you got your results on many slides, so do you have a graph or a slide that
This
slide, I think we are just putting all the graphs together, but
Yes.
do you have like maybe some correlations between how the frequency, like how the two things correlates? Like
No,
maybe like
I put them on different graphs, sorry.
So can you show me the
Okay.
graph, please?
I can start from here. Okay, so we can look at this one first. So you want to know the correlation between the frequency and
And like, so when the frequency change, how the amplitude would change?
how the amplitude change. Oh, okay. So as the amplitude, which amplitude are you talking about? Do you mean the rotational amplitude or the longitudinal?
You said the blue one.
Yes.
The blue one is your
Longitudinal.
amplify the motion, right? So in your previous graph you showed that for if the frequency is very big, so you actually can't really see these sine waves.
Oh, it is because I'll turn back to my theory. So it is here. It is a combination of two of the cosines, and here is the resulting here's the resulting graph that will occur, and this fits quite well with what we got from our experiment.
So this is for the amplifier, so I mean like so if you squeeze the
Oh, you mean this one?
yes, then so you're like this. So did you make the graph like in this condition?
Oh yes. Let me turn to my data analysis. Okay. Actually, we can see from here. So starting here, the frequency isn't that high, so it's not as compressed. But as you can see, the trend goes on. We can see that it starts to get more and more compressed.
So what can you explain by seems like when the red amplitude decreases, the blue one increases.
Yes. This is due to the energy transfer. And for the I'll turn to this page. So for the blue one, we can start. We started off by giving it a longitudinal displacement. So all of the energy we can say that it was in the longitudinal direction. And as time goes by, because it is coupled together, some of the energy will start to transfer over to the rotational side. And we can observe from this experiment here, it starts from 0 and it starts to, the amplitude starts to increase. And the longitudinal one starts to decrease.
Okay, thank you. And the next question is, so since you always do the same spring and the same mass, did you ever thought about maybe changing the spring constant may affect the phenomenon?
Okay, so for this, I'll also turn back to my theory. Okay, so you said, did I consider changing the spring and changing the spring constant, right?
In your experiment.
Oh, in the experiment. I did want to do this, but I think we can also change the moment of inertia, and that will also affect the natural frequency. And if we change the spring constant, we can also obtain the same results. We can also change the natural frequencies from changing the spring constant.
And so in your experiment, did you make sure that the mass hanging on the pendulum and the spring is stable enough? Because there might be a lag between.
Oh, so it means did I secure the connection?
Yes.
Yes, I did.
How did you do that?
We used we first used a string to secure the connection, and also a bit of hot glue gun to secure the connection.
But bubblegum is actually like, squishy, so
Uh,
I don't
it,
think
I,
that it's.
it will fill the gap between it, and from our experiments, it was pretty secure.
Can you explain the reason on your graph there is an amplitude decaying?
Oh, and uncertain decay. Okay, so for this, let's first take a look at our experiment. Okay, so you mean this amplitude starts to decay, right?
Yes.
I think this is due to many factors, mainly the friction and also different drag forces in our realistic experiment. Maybe some of the connection points, some energy will be lost there, so the amplitude will start to decay over time.
So, can you clarify the amount of the decay?
No, sorry. I think it may vary from experiment to experiment. So we didn't, we didn't really quantify or control this factor.
So, can you say it's because of air resistance or?
Also some friction in some of the connection points.
Another question, in this picture we can see like, how did you hang the spring on the top?
I also used a similar way of securing the spring to the to this tube. So I also used some strings and also some hot glue gun to attach it.
So to the previous question, you say the energy decay is due to some friction or resistance. So did you consider it in your theory and your equation?
No, I didn't consider it in my theory or.
So just a transition. So since K is like a sum of maybe the radius of the spring and the length and many things. So can you make a prediction of like how the radius of the spring can affect the rotational energy that is transferred?
Oh, okay. I think the spring's radius may affect the physical attributes of the spring itself. Maybe it will change the spring's constant and then affect the natural sequences.
So, do you think it will increase with the radius or?
What will increase with the radius?
Like when the radius decreases and the energy transferred into rotational energy will.
Do you mean the time or the amount of energy?
The amount of energy.
That is I don't think that is the main reason for the energy transfer.
Okay, the time is up. Please summarize the discussion.
So first extent is their external setup is stable because there is a tilt angle of the rod between the rod and forward, and they say it might be caused by footage tilt angle or it might be caused by the footage. And ask them about their frequency and correlation, and he showed me the graphs, and it is explained pretty well. And I asked them if they consider different spring constant, and they say the spring constant is affects the phenomenon same as the other parameter that they have done, so they did not do the spring constant.
Okay. The reviewer, please.
Okay, so first to the reporter, could you show me an intuitive explanation on like the effect of between theta and z, like in the force?
In the force.
So turn to your theory where you analyze the force.
Yeah.
So can you give me an intuitive explanation in why, when there is a longitudinal motion, the theta also affects this motion?
So do you mean the theta here affects
Yeah.
the whole
Yeah.
motion?
Yes.
So the theta is for the rotational motion.
Why? Why is it connected between these?
Okay, so we connected this mass to the spring, right? And it is because of the spring structure, so we can couple these two.
Could you give a more thorough explanation in how they were coupled?
How they were coupled? Because we connected the mass to the spring, so when it's spinning, as I said in the here, you can see that when it's
Okay, thank you. So also, why is it proportional? Like in your theory, you just assume that these two forces are proportional. Like you just use a constant times d theta. But how did you derive this form?
this is from the research paper.
And did you do any like confirmation of this theory? So
I checked with multiple sources, and they all came to the same conclusion.
okay. And is there a page where you compared your theory and your experiment?
Okay, my theory and experiment. Mainly I compare it here. So we can.
So in your theory graph, the amplitude, so the amplitude decreases to 0 in your theory, but then in your experiment, so show your experiment data.
Okay.
So in your experiment data, there still are some amplitudes when these two forces correlate. Could you give an explanation? Like in your theory, it decays to 0, and then.
Do you mean for the blue one?
Yeah.
Oh, so in this here, we can see that the amplitude difference also affects this, whether or not it will go to 0, and as we can see in this.
Okay. So also two of you, like the opponent and the reporter, you both. So you were discussing on energy decay. So you said that energy decay. You didn't analyze the energy decay. How do you think that the energy decay would act in this whole motion, like compared to the theory?
How would it affect
this system?
I mainly think that only the amplitudes would be affected.
And did you analyze like which kind of function is the decay? Is it exponential?
I think it might be an exponential.
Okay, how about the opponent?
I think I agree with your word.
Okay. Thank you. I'm going to read and fellow competitors. This is the reviewer from Team Miracle, and I'll be reviewing problem number 12. So this is the introduction of the problem, and the reviewer believes that the focus should be like the torque effect on the whole spring system, and what is the correlation between the rotation and the stretch, which the reporter doesn't clearly explain. So this is the outline of the reporter. So for the phenomenon, they describe a change between the longitudinal and the rotational motion. And for their theory, there are three terms: the longitudinal, the rotational, and the coupling. However, the reporter doesn't clearly explain the coupling, and they also use a normal mode to derive their equations. However, there are some problems to this. And also, in their experiment, there are two things that they did. The first one is the different amplitudes, and the second one is different initial conditions. So there are some good things that the reporter did, which is they did a clear display of this phenomenon, and there were a lot of videos showing it. And however, they failed to compare the reality and the theory, and also there are some problems in their theory. And also they failed to analyze other motions such as the initial condition. For example, if you tilt the system a little bit, and also their experiment doesn't really 100% fit the theory. However, they didn't give a clear explanation on this. So for the opponent, in their presentation, they summarized the report. So there are some. So they gave a very clear summary of the reporter's report, and also they find some questions in the setup. However, they didn't bring up the pros and cons of the report, and also they didn't have a lot of questions relating to the derive of this theory, and also their time management in the discussion. So in their discussion, first, the opponent asked why this is tilted, and the report believes it is a setup. And the reviewer also agrees with the report, since I believe that this is not really, this is just a small error in the experiment. Also, okay, so the next one is there a comparison between the graphs? And there is not such a graph according to the report. And the reviewer believes that this should be included to give a more intuitive explanation between these phenomena. And also, the amplitude and frequency relations in this experiment, the reporter thinks that it is not very important. However, the reviewer believes that there also should not be too much of a relation between the amplitude and frequency. Okay, next, so the change in the spring constant. So the reporter believes that by changing the mass and the inertia, it could also change the natural frequency, which the spring constant is connected to. And the reviewer also agrees with this. However, so the reviewer also agrees with this. Okay, so the energy decay. The reporter believes that it is due to friction and air drag, and the reviewer agrees that these two terms do in fact affect this system, and also there should be damping effect in the spring. And the reviewer believes that the reporter should do some analysis in this part. So there are some points that they missed. So first is the stretching model of the string, which is used to explain the coupling term, which when the reviewer asked the reporter, they didn't give a very conclusive explanation, where there should be a correlation when the spring stretches, the radius of this spring also changes. So there will be a torque that the string wants to recover to its original state. And also the natural frequency between the omega z and the omega theta, which is used in the normal mode derived. However, in their experiment, these two natural frequencies is different, which means that there should be some problems in their theory. Next will be the energy, other motions like the reporter just said, and also some couple measurement, and also one very important is also the energy decay, which they didn't analyze. And they should also do some comparison between the reality and the theory, and also the mass of the string is not considered. Thank you.
Okay. Concluding remark from the reporter.
Okay, so here is my concluding remark. So for this question, did you change any more parameters such as the spring or the mass? So for this question, since the natural frequency, I only want to investigate the relationship between the longitudinal natural frequency and also the rotational natural frequency. So I think if we change the moment of inertia, we can also change the relationships between the two natural frequencies. But I think this is a good suggestion, and maybe I can try to add these parameters maybe in in the future. And also another thing is about this. So I think sometimes they've asked about why the amplitude doesn't go to 0, and this is because of the difference of amplitudes between the two cosines, and this is what causes the amplitude to not doesn't go to 0. And okay, and also for our experiment data, we can see that for the blue one, it actually, I think it fits quite well with the our theoretical model, which is that the different amplitudes of the cosines will also result in a similar graph of the blue one. And also, the final one is also the I think the reviewer said the stretch of the spring. So I mentioned here that when it's pulled down, the spring uncoils, and when it's compressed, the spring recoils. And this will cause a torque on the mass, causing it to rotate. Thank you.
Okay, the time is up, so let's now take questions from the jury.
Just want to make sure this is the problem case investigate the behavior of such pendulum and the relevant parameters. Right? So
yes.
According to the problem, what should be the most relevant parameters we should investigate? That question holds.
Okay. So for the relevant parameters, the main parameter is the natural frequency, and we can change this by changing the moment of inertia or the mass and such things.
I believe it's the natural frequency, so like the kappa constant and the K in that formula.
The more detail, the parameter.
The parameters. So they could change like different kappa constants of the string, like using different strings and different kappa constants.
I agree with the reviewer.
I have a question for the reporter. Why you just change the moment of inertia in the experiment?
Okay. Okay. So why did I only change the moment of inertia? Okay.
You
So.
didn't try to change the mass.
Okay. So here are the natural frequencies, and I think this is the main parameter in this experiment. So when I change the moment of inertia, it will also change the natural frequency, and thus it will be changing the relationship between the omega longitudinal and also the rotational. So that's why I changed the moment of inertia.
My question is why only change that?
Oh, huh?
Why only change the moment?
Oh, why only change it?
You didn't try to change the mass? That will do a similar thing.
Okay. I didn't change the mass because it also changes the moment of inertia, and then there will be two variables changing. So I think I can. I think if I only change the moment of inertia, I think it's a better way to do my experiment.
Okay, but in all your experiments, you didn't give us the coupling constant. You should be able to get the coupling constant.
Oh, I didn't. I didn't calculate the constant yet, but the constant will become smaller in our experiment.
Very small.
I said it will become smaller, but how small? I think I'll have to do some calculations on it.
How do you think is coupling constant important or not?
I think the coupling constant is in fact very important because in the theory so the coupling constant is one of the most important reasons why there is a transition between those two energies. So this should be a very important factor that should be calculated in the experiment.
How do you think?
I agree with the reviewer because that is also what I think the phenomenon is going about.
Any other questions from the viewer? Okay, then let's move on with the grade. Finished. Okay. So now let's show the grades for the reporter first. Starting from me, it's 7, 7, 5, 5, 9, and 7. And next for the opponent. Starting from me, 4.
Opponent, sorry.
Opponent.
Yeah.
Opponent. Okay. Starting from me, 4, 5, 5, 5, 5, and 4. And finally, with the reviewer. Okay, starting from me, 8, 8, 7, 8, 8, and 8. Okay, any comments from the
Marvin, I think Marvin said the relevant parameters for this phenomenon. The phenomenon refers to the oscillation, also rotation. So that the most important parameter should be the localization of the swing. For example, the pitch, the radius. Right? I think that should be the main focus. Instead of all those parameters, your mass or whatever. Because this phenomenon will persist whatever the mass you use.
any other?
I have completed all of them first, especially sports and reviewer, because you get a very good competition on this parts. Because I have graded this one before. I have consideration for the recorder for the first part, even you did not answer it correct, did not answer completely, not actually corrected but not completely. The topic constant will be the most important part in this question because that occurs by the reviewer and the opponent set, and that will be the curse of the end potential between those two modes. However, you have demonstrated that when you put the spring down and it does rotate, it means the change of the z direction would curse the rotation part of this one. But you demonstrate that, but you did not give the quantitative estimation. If you give that quantitative estimation, that's great. That means you completely solve the problem. Okay? And other part of the reviewer pointed out a few very good questions of your problem, but it doesn't matter. Once you catch that part, even you use only the normal mode, because all other motions are linear combination of those two modes. Right? And you will, if you can focus on the carbon constant, of course that will be the curse of because it springs down, the radius of the spring will shrink. Okay. If you can complete that calculation and that you get, maybe you will get 10.
Okay. I would also like to add that, for example, if we can consider the sum of the two normal modes, I mean, if you take the square of the frequency, then that would be independent of the coupling. And you should at least try to show that this is consistent with your data, right? You didn't do a lot of data analysis. You just sort of do the direct calculation. And also the energy dissipation, you should also try to study that. Okay, so let's conclude this stage. You're supposed to challenge. Yeah.
The opponent challenges problem number 4, wind speed.
Problem number 4, wind speed. Rejected. Okay.
The opponent challenges problem number 15, rebounding capsule.
Problem number 15. Okay, problem number 15. Please write down the name of your representative on the record.
Chairman，
Yeah.
这连线好像一直很不稳定。
我换他电脑有看到，就是他有插一些进去，但扣进去。
换了2个选接头好像不行。还是我自己有带 H 线我要试试看。
可以啊，如果你有 HDMI 线，你可以换一下。他们刚在这里，你们是 opponent 吗？对，刚前2个 opponent 都没什么问题。
可以啊，可以啊。你说 H 线直接对。对。
够长。
可以吧？
这个题目嘛，对不对？好，最后选的题目这些资讯。
我们这边吗？
对啊，对。
那个系班那边会给我们那个一张表。
Okay, please.
Honored juries and competitors, I'm Sherfair from Untitled, and now I'm presenting problem 15, rebounding capsule. So first of all, I would like to talk about the problem statement. The problem statement says a spherical ball dropped onto a hard surface will never rebound to the release height, even if it has an initial spin. But a capsule-shaped object, on the other hand, may exceed the initial height. So there is my highlights. So about spherical ball, it means the object that cannot rebound to the release height is spherical symmetry. And to the initial spin means its initial angular velocity does not equal to 0. And in capsule-shaped object and the initial height, we will see the definition in the following. So about the capsule, its definition is a 3-dimensional geometric shape consisting of a cylinder with hemispherical ends, which means it is a cylinder with 2 hemispheres. And about the initial height, we would consider the initial height as the relative maximum of the trajectory. So to exceed the initial height, we will not consider about the releasing height, but every rebounds. So for our initial height, we'll be finding trajectories like this. So it exceeds the initial height, because we consider that when it is on the maximum point, it shouldn't have kinetic energy. So it will just be pure rotational energy and gravitational energy. So that would just mean the same thing to when we release it with different height and different initial angular velocities. So I would like to separate the rebounding circumstances. So first of all, depends on how it lands on the floor. So the red part means the torque direction. So it means when it's turning that way, then it could be hitting it. So for the left-hand one, it means that the end of the capsule with the higher relative velocity to the ground hits before the other end, and vice versa. And then after they hit the ground, they rebound. So the four conditions will be the two on the top, and whether it changes rotating direction after it rebounds or not. So here's the force about when the capsule contacts the ground. So there's mg, there's positive force, and there's friction. So I would like to focus on the positive force, which makes a torque on the capsule. And the two condition differs from the direction of the end will make a different direction of torque to the capsule. So in this condition, the torque that N made to the capsule will make it turn faster, make it rotate faster, and this will slow it down. So when the capsule is in the air, there are three energies. So there's gravitational, rotational, and kinetic. So since it says to exceed initial height, it means, so the gravitational energy's definition is mgh. So since m and g stays constant, then the gravitational energy would be positive correlated to the height. So which means when there is no kinetic energy, then how it exceeds the initial height is because there is a rotational energy which converted into gravitational energy. So for every point, every t in the capsule when it's flying in the air, the energy sum will be the initial energy sum minus the energy loss in the path going. So here we can get the energy sum with the definition of the three energies. So there is some variables. We got m, g, which is constant, and then for omega, h, and v, we will get it from our experiment. So now we need I, which is the rotational inertia. So for the rotational inertia, we get this rotational inertia with the axis, like the picture here. There's x, y, and z, and by measuring the outer radius and the inner radius of the ping pong, we got the ix we need here, which is rotating by the x-axis. And so this is our experiment setup. We glue two ping pongs together and consider it as a capsule, and we put it on a test decoder, and then we give it a force like that. And here's our data. So the upper graph shows the velocity on the x-axis and the y-axis. So on the y-axis, you can see it's a motion with a constant acceleration, which we can see on the third graph. And those points that increase means it hits the floor. So the acceleration increased to make it rebounds. And there is velocity on the x-axis, and there is a obvious increasement, and we will consider that is affected by the friction we talked about in the before's graph. So the friction makes the velocity on the x-axis change. And so I picked out those acceleration on the y-axis out, and then I get the average, and it is negative 10.2, and which is, I think it's close to the G we know, which is 9.8. And here's our three energy. The upper one is rotation energy, the lower is kinetic, and the gravitational. So I got the red lines like this, so to tag the rebouncing part. So we can see through the rotational energy for each rebound, after rebounds and before the second rebound, it stays constant. So it means that it spins at a constant speed, which is related to the conservation of angular momentum. And then the kinetic energy would be about the velocity, and which is a concave up parabola for each flow when it is in the air. So I sum up the three energy, and you can see that it stays constant when it's in the air, and when it hits the ground, I would say that the energy is given to the ground, and then the ground gives it back. So there is a rapid decrease and then increasement. And consider about we use ping pong, so air resistance would be a cause about the a slightly decrease of the sum of energy, which is the red line on each flow. But I think it's more obvious on the right side. And we can see that before every time it rebounds higher, it mostly has a big difference on the rotational energy, and then it rebounds higher. And since the rotational energy increased rapidly, the total energy decreased a lot. And so we would like to find the correlation between how these two interact. So it's about the COR. So we calculate the COR by finding the ratio, and it's true, of the sum of energy before and after each rebound. And so we got those data, and we made a fitting line. And this pretty much matches our theory, because when the contact angle is 90 degrees, which means it is more, which means the end hits the ground lighter, so there should be less energy loss. And so from 0 to 90 degrees, it is a increasement as the angle increases. And I think that is it. Thank you.
Okay.
Okay, so here are some questions for you. First, your way to your definition of a capsule. Can you show me your definition of a capsule? Yes, a capsule is a three-dimensional geometric shape consisting of a cylinder with a hemispherical end. And can you show your actual capsule, what you used in your experiment? I assume that you used a ping pong ball, right?
Yes.
Do you think that matches up your definition of a capsule? I don't see like any cylindrical connecting the two hemispherical ends.
Because in the aspect of it hitting the floor is always the tangent line of the hemisphere.
Okay, so you're saying that the contact point is always on the hemisphere.
I mean,
So it doesn't matter.
to the extent of hitting the floor, it doesn't matter, but the airflow might matter.
Okay, okay. And next, page 3, please. Okay, so in this, this is the track of your central mass.
Yes.
Your meaning of rebounding of a higher height, does it mean that it rebounds from higher than the initial height, or just a previous? It can also be considered as a.
We will say than the previous.
Okay. And next, in your theory, you have a normal force and friction. Have you ever considered calculating the normal force and the friction? And do you know if it's a static friction or a kinetic friction?
We chose not to calculate the force because I think it is more based on energy, and that would be an easier way.
Okay, thank you. And finally, how do you release your capsule? Okay, so by hand, right? Okay, thank you. Professors and fellow competitors, I'm the opponent from Team Miracle opposing problem number 15 rebounding capsule. So first, let us have the overview of the report. The phenomenon. The reporter says that it rebounds higher than previous at a certain height, and in the theory, the reporter considered an energy loss and considered friction, but does not discuss how the friction matters on it. And on the setup, the reporter used two ping pong balls stick to each other, but I think, but the opponent believes that it is a contradiction for its definition of a real capsule since that there's a structural difference between the two systems. And next, the reporter said that she uses her hand to release, and the opponent believes that it is unable to control the parameters. And finally, to the experiment, the reporter shows field data and does not match with the theory. Here are pros and cons. First, the reporter gives a clear schematic diagram showing how the capsule rebounds. And next, some clear graphs explaining the phenomenon, which, as we can see in the center of mass, it actually bounces higher than the previous. And so here are the cons. First, the reporter gives an unprecedented theory, which does not have considered the parameters and plug it in and compare it with the experiment. And next, the reporter spends too much time on simple concepts such as the energy transfer between the kinetic energy and the potential energy, and the energy loss and the moment of inertia. And next, the reporter does not give any intuitive explanation, any quantitative explanation, and any qualitative explanation to let us know in what conditions does it rebound higher. And next, as I said, the reporter does not thoroughly explain the phenomenon. And next, the reporter gives an informative, messy, and unclear graphs without explanation, as we can see in the energy and velocity. And the parameters are unchanged and unable to control. And finally, the opponent believes that it's a problematic experiment. So about the theory, we're going to be discussed about the energy and the energy loss of friction, and the magnitude and direction of the friction. And next, I want to discuss about the angular momentum of the total system and the elasticity of the capsule and the restitution coefficient. And about the rebound conditions, I want to discuss about the dependency on certain parameters such as velocity, angular velocity, and contact angle, and some critical conditions of the rebounding, that the capsule can rebound higher, and some contact angle limitations when the angular velocity of the capsule is too high, there is some contact angle limitation because of the geometry. And finally, the material limitation of the capsule itself. And on the capsule itself, I want to discuss the structural difference between a capsule and the ball, and the structural difference between a real capsule as the reporter defines and her actual capsule using in the experiment, and the moment of inertia of the capsule. And finally, on the experiment, I would like to discuss how to control of the initial conditions such as velocity, angular velocity, and finally contact angle. And I would like to start my discussion. Okay, so first on is about the energy. Can you show the page where there is a energy graph and page? I'm sorry, I don't know page, but you can see that the energy drops down a little and bounces back during the bouncing. Yes, this one. As you can see, here okay. So can you show me where does the at which point the capsule drops onto the ground?
On this point, which is the lowest.
Okay, so the frame. Can you tell me what is approximate time of its contact time?
We cannot get that because we have because of FPS was too slow, so was too low, so we cannot really get the.
Okay, can you tell me what is the FPS of your camera?
It should be 24.
24.
240 FPS, but it has to be converted from MOV to MP4, so there should be a compression.
Okay.
So it should be lower than.
Okay, so I'm assuming that the contact time is from here when the potential energy drops and goes back. Do you agree with me?
I think if you assume that like that, it would be the contact time would be a bit too much.
Okay, but you're saying that you're sure that the contact, when at this point at this time the ball contacts to the ground, right?
Closest to that point.
Okay. Next, do you think that the friction and what do you think that the friction actually does on the capsule?
care because when in an ideal condition, if you throw anything with a initial horizontal velocity, it shouldn't change. But in this case, we can see it increasing and it decreasing.
Okay, so you're saying that what friction does is to only decrease the horizontal velocity. Is that correct?
Decrease and increase.
Okay, so you're saying that the friction does not have any contribute on the torque and the angular momentum of the capsule. Is that correct?
No, I think there is, but we didn't calculate that.
Okay, so
I think that is probably relatively small to the one that positive force gave it.
Okay, so you're saying that you think that the main force that changes the angular momentum is the normal force, not the friction.
The positive force.
Positive force. What?
Normal force. I think it's the same.
Yeah. Okay. Next, I'm going to discuss the rebound conditions. And first, can you say in what conditions can the capsule bound higher than the previous height?
There's a lack of our experience on that, but I think we can improve that by rearranging our experiment data and things. And it should be some correlation between not only by the contact angle, but the contact angle and the rotational, the contact angle and the rotational energy, both. And there should be a ratio.
The rotational energy. Do you mean that the rotational energy is constructed by the moment of inertia and the velocity, the angular velocity? Do you think that what matters most, the moment of inertia or the speed of the angular velocity?
I think it matters. I think the ratio matters.
The ratio matters. So you're saying that if you have if you have a small moment of inertia but with a high angular velocity, it will rebound higher. And conversely, if you have a very high moment of inertia but a slow angular velocity, it will still rebound higher. Is that correct?
I thought we were talking about angular velocity and the contact angle.
Yeah, I'm saying that. The first question I'm asking you is that the dependency on certain parameters that make it to rebound higher than its previous height. Yes. And you're saying that you think that the contact angle and the angular energy is the main factor. So
Sir, I think I have to correct
yes.
my words. I think it's the correlation between angular velocity and the contact angle.
Okay, so can you give it an intuitive explanation of under what conditions can it rebound higher than the previous height?
Do you want accurate numbers?
No, just like a qualitative explanation.
So I think when the angular velocity increase a lot and then it rebounds, it is more likely to go higher.
And about the contact angle?
I think the contact angle, with a smaller contact angle, the angular velocity can be better converted into kinetic energy.
Okay, so please.
But also more energy loss.
Yes. Okay. So please go to back please. Have I ever considered one case where okay, so here is your capsule light. When its angular velocity is in this direction, but the contact point is here. So it tends to goes up, but because of the higher of the linear velocity, its contact point connects here. Do you think that what do you think is the consequence of this case?
For this case, mostly because the friction goes.
Let me ask you another question. Do you think that the linear velocity of the center of mass matters if to the phenomenon?
I think it matters, but we will be considering the.
Can you say how it matters about how it affects the phenomenon? linear velocity?
The linear velocity affects the relative velocity by the end of the capsule and the ground.
Okay, so you think that if it's a higher linear velocity, it would go higher, right? Okay, so my thought on this is that the linear velocity, if the linear velocity is very high, it would not always be in this condition where the contact angle is at the same direction as the angular. And in this case, most cases, this will make it rebound higher. But in this case, if you have a very high linear velocity, it would in some cases the contact point is here, but the rotational velocity is here. So it actually is not crashing into the ground, but only a touching. So it will not go higher than the previous time. So this is what I thought about the effect of the linear velocity. Do you agree?
I think this point would be, I can make some correction on the last graph I made. So it's not only about the contact angle.
Okay. Next on, so do you notice that there is an angle limitation on the cases where you have a high angle velocity? What I'm saying is that if you have a very, very high angle velocity, it would definitely not drop in a small contact angle.
You mean because it's
because
the
this
contact
case,
time is too long?
no. Because if you have a very high angle velocity, this would not happen, because if this would happen, this case would happen before. So the velocity, the contact angle will always be will always be at a certain angle, not below a certain angle. Have you ever observed this phenomenon?
So that means it didn't spin over half a circle, and then the other end hits the ground, right?
Oh. Yes.
We consider it as so we think that is about the center of mass. So it will be a very little bounce.
Okay. And next, on the capsule, do you think that there is a structural difference between your capsule and the actual capsule and your experiment that two capsules connect together?
Yes, there is, but in my opinion, to the method of contacting, this one will always be.
Yes, I understand that it will always contact here, but my thing is that it is the structural difference. You see, the connecting point is always here, but no, not only moment of it will affect how the force goes through the entire capsule. If it's a real capsule, it's all solid here, but in your experiment, you stuck it here. So I think that the phenomenon would be quite different if you use a real capsule.
I think our ping pong is hard enough, so that wasn't that is negligible to our data.
Okay, thank you. So to conclude, to begin with, we first discussed on the energy. The opponent sees a quite weird phenomenon here, where you can see the energy drops down, but drops down in a certain frame, in a certain range of frame, but the reporter cannot ensure if it's the actual contact time. And next, on friction, the opponent and the reporter has agreement on the friction that it also causes a angular momentum to change. But the reporter thinks that what really matters is the Wilberforce. But in the opponent's point of view, we believe that friction also matters a lot, and it is important to check if the friction, what is coefficient of friction, and what is the actual contribution of the friction. And we discussed about the dependency on certain parameters. The reporter shows that she said that she uses.
Sorry. Now, the reliever.
Honorable judges and fellow competitors and today's reviewer from Team Google, I'm the Newton. So thanks the report's presentation and the opponent's good question. I have some question for the reporter. The first is, what did you think will be the motion when there is no friction force? Because in your theory model, you have said that a friction force will cause the tick a ping pong ball to bounce, right?
Yes.
So what do you think it will be the motion when there's no friction force?
We consider friction force because we assumed that it is a fixed point. It didn't drag.
Yes, I mean that if there is no friction force, but with the
If there is no friction force, then every time the capsule drops to the ground, there will be, because the center of mass will go down. So every time it hits the ground, the two ends will both hit the ground.
Okay, I'm going to say also, what is your opinion?
Oh, okay. So I think that the friction also matters a lot to the grounding condition. So if there's no friction, it's possible that it will not rebound to be higher than the previous, because a friction also has a friction can also convert to decrease the angular momentum and change it to a velocity.
Okay, I understand. So the second question would be, there is a horizontal velocity when the capsule contacts the surface.
Yes.
Yeah, so do you think that the direction of it will be any difference in condition friction and in condition without friction?
Yes, it will. For there is friction means there is a fixed point. So the center of mass may be going in an arc, but if they're not, it just be simple, just drop and with a fixed horizontal velocity and.
I'm sorry, can you rephrase yours?
So there is a horizontal velocity. So do you think that the direction of it will be any difference in the conditions with friction and in conditions with?
Yes, I think it will, because the horizontal velocity actually has a contribution to the velocity of the contact point to the surface, and the velocity of the contact point to the surface will determine whether the friction is a static friction or a kinetic friction, and resulting a different magnitude of friction.
Okay, I understand. Also, so that is my question. so I'm the reviewer from Team Google, and now I'm going to review the problem number 15, rebounding capsule. So the problem statement, the opponent and reporter have discussed about it, so I won't tell about it. So here comes the summary and comments of the report. So the phenomenon in the report that it said a capsule should shape object rebound height may exceed its initial height, and laws apply to torque and energy and COR. And the experiments with the report is that the changing factor the report only do is that a different rebounding circumstances and setup is two ping pong balls connected together, and also a camera to show this. So in the conclusion, the correct correlation between contact angle and angular velocity is the main factor for the capsule to rebound and exceed its initial pace. And there are 4 rebounding circumstances. Some advantages and suggestions for the report and have a good thing is that many diagrams and consider energy loads grabs off the motion to clearly see the rebound. And the suggestion is lack of parameters. You can see the rebounding capsule more in different ways. And here is a summary and comment of the opponents. So the advantages there is many details about the experiments and theory are considered and acts about many conditions. So here's the summary and discussion between the report and the opponent. So in the first question, the opponent has reported that do you think 2 ping pong balls can be used as in capsules? Reporter asks yes, and yes, the technical line is the same. But in my opinion, I think that the capsule still differs from 2 ping pong balls like the airflow around it. Maybe using a capsule shape will suit its problem better. The second question will be what does the friction force do on the capsule? The reporter answered that it will change the horizontal velocity and torque and rotational energy. In my opinion, it will give the capsule torque and change the movements of the capsule. So in the conclusions for my question to both of them is what do you think will happen if there is no friction force? Reporter answered that I think both ends of the capsule will both hit the ground. And the opponent answered me that it may not exceed the initial height. So in my question number 2 is that do you think the horizontal velocity will change due to friction? The reporter answered me that I think both ends of the capsule will both hit the ground, and the opponent answered yes, it will. But I think the direction will be constructed in the 2 different conditions. So that's my view for the rebounding capsule. Thank you.
Okay. Concluding remarks.
So here's some concluding remarks about both the reviewer and opponent have mentioned the structural difference between capsule and device. So as I said, the airflow may be different, and on the aspect of contacting it doesn't matter. And another thing I would like to mention is that when we are calculating our moment of inertia, we consider it as a hollow spherical ball, which matches our condition of 2 ping pong connected together. And about the linear velocity the opponent talked about, I think we will consider it as part of the related velocity from the end to the contact ground, and that is the part we can improve. And maybe next time we can use a footage with higher FPS, so we can get more parameters, such as the contact time and how it can affect the phenomenon. And the opponent asked us to give an explanation about why it rebounds is higher, and I think we've talked about before circumstances, but maybe we should analyze each condition more, and that is the part we can improve. And also having a fixed initial condition or on different parameters and independent and dependent parameters. Thank you.
Question from the jury. Anyone? Yes?
From the opponent to the viewer, to the reporter, can you think about a way that you can change the contact angle? The way to change can you try to find a way that you can change the contact angle?
Alright, so if a given a constant angular velocity, you can change the initial height, because if you always put on this.
Let's go to the next one.
Okay.
How do you control the angle velocity?
Well, I actually don't have a.
I think it may change the release angle and change the release angle. Yes.
Change the release angle. Okay.
That is the reason why we separate the set of data into different parts. So for each different parts, there is a different angular velocity.
So you just keep bouncing and check the bouncing for the angle is different. Okay.
Any other question from the jury member?
Why you use two ping pong ball instead of USB?
Because we think we have considered about using a tick banding, but first of all, it's too small. So when you're tracking the data, I think it might differ a lot from the accurate one, since it's too small, and I don't think a tick banding is really fitting the really fitting the definition of a cylinder.
What do you think the disadvantage of using ping pong ball?
Sorry, can you repeat?
Disadvantage of using a ping pong ball.
Okay, so I think this is from the first point. It is different from what the current statement stated. So a ping pong ball, the structure of a ping pong ball is two balls, separated balls, and connected with one point. But a actual capsule is a capsule of a solid capsule, and like all the points is connected and continuously together.
So
just a moment. Have you finished your question?
So in my opinion, that using a ping pong ball, there may be an airflow to flow over the ping pong ball. And I think that maybe we can make a bigger tick banding that will have a two choice question. Yes.
Okay, what is the shape? Any other question? Okay, then let's move on with the grading. Everyone done with the grading? Okay. Now for the reporter. Starting from me, 4, 5, 5, 5, 5, and 5. And then for the opponent, okay, again from me, 7, 8, 7, 7, 7, and 7. Finally, for the reviewer, 5, 7, 6, 7, 7 and 7. Okay, any juror would like to make a remark? No? Any questions from the student about the grade?
You can check.
Okay, if not, then let's conclude this session.